and thanks for having me around here. So I'm living in Berlin currently, but I'm working in Hamburg. I'm the Vice President Data Science for a company in Germany called XING. XING is the LinkedIn of the German-speaking countries. It's actually the market leader. It's a social professional network. We gather around 15 million subscribers in Germany, Austria, and this is my presentation. Yeah, in Germany, Austria, and Switzerland. And we have around 2 million weekly active users. So it's a professional social network. We're basically connecting people together. We have a job portal, news business, et cetera, et cetera. The company exists for 15 years. It's actually quite a successful company. It's kind of an oddity that we manage still to resist against LinkedIn. We are around 1,600 employees, and I'm driving the data science department. So we're around 60 data scientists and data engineers. And we are doing mostly bringing those algorithms that you heard about into production at scale for the benefit of our users. And have the focus I want to have today is on productivizing machine learning at scale, because at the end, sadly, the algorithm does not really matter. If you want to have an impact on user, what matters is engineering and business, but I will come back on that in a minute. It's obviously slightly provocative. So I'm not a computer scientist by background. I'm actually an astrophysicist. I've been an astrophysicist for 15 years. That's me on the top of a summit in Chile, in La Silla, in front of a telescope entity. I lived in many different countries. I actually spent 7 years in Asia. I was a professor at the university in Shanghai as a Qinyan in Jiaoqiu, which is quite a prestigious position there. But what I was doing in astronomy was basically dealing with data, and a lot of it, far more than what you can imagine. And I decided a few years back to do a switch, and for the past 4 years I've been managing teams of decent size in companies such as OLX, that you probably know here, Scout24 in Germany, and now XING. So XING, as I mentioned before, it's a professional social network. And one of the things that we're trying to do is to bring basically benefit to our users to use the services, connect them together, recommend them other users, so helping them searching other users, recommending jobs, and all that requires a lot of the things we heard today. So we are basically working with deep learning. We have a very complex ontology, because when you want to match CVs, for instance, and job advertisement, you need to understand the text. So we're doing quite a lot of NLP and ontology building. We want to understand our user better, so we worked a lot around user modeling, for instance. And all of this is based on machine learning. And, well, this is the AI part of my slides, according to Vladimir. But it's basically machine learning, actually, and AI is there. And it's basically present in every single part of our life, and it's getting more and more there. But there's no magic behind it. It's purely actually engineering, and the difficulties there is not only to develop the right algorithms, understand how they work, it's to bring them at scales in production that they work every single time for all the users. And when you're a Facebook or a Google, that really matters. Despite that, we're still at the start of it. It's the prehistory of AI. We are still haven't unleashed the lions or the tiger there. There's a lot of limitations out there. And the limitations that we have are algorithmic, but again, mostly engineering-wise. And in terms of what is the span of technology that we're using today in terms of machine learning, we have explored only a tiny part. And this tiny part is called supervised machine learning. And supervised machine learning is what makes up around 90% of the algorithms that use in any of the technologies today. And this is limiting us. So we had huge progress that happened in the past 10 years, in particular thanks to neural networks. So this is Andrew Ng. If you don't know him, it's the guy that created Coursera, and it's probably the most popular machine learning classes in the world. Probably several hundreds of thousands of people, if not millions, have been following his classes. And one of the things that he realized is that the power on neural network, which is a technology is rather old actually, it's from the 50s or 60s, but the power that we have is that it scales. very rapidly. So the plot that you have here is the performances of your model compared to the size of your data. And the more data you have, the more you can fit to your model, the more performant your neural network will be. So we need to, for instance, use a large corpus of text to train word-to-vec. The importance here is, again, the data. And in a lot of cases, that's good. I'm working in the internet industry. That's great. We have tons of data. I was doing astronomy before. Again, lots of data. That's great. There are cases that it's a bit more, for which is a bit more difficult in healthcare, for instance, where the sample size are smaller. And sometimes you're in a regime where statistical learning or old-fashioned machine learning is actually more powerful than those very greedy, neural networks. The other problem is, we had a bit of a glimpse in two previous presentations, but it's actually what is, when you want to bring this solution at scale, is the biggest problem. Is that you have a full cycle of learning there, and what you're going to spend your time on as a machine learning engineer or a data scientist is actually of everything but training your model. You need to collect the data, knowing if the data is there. Usually what you have as a data source is a pile of shit. So you need to clean it, you need to extract the information, and need you to understand that. Probably you need also to do some feature engineering, dimension reduction, etc., before you can really start playing around it. And then it's not the end of the story, because you have the learning phase. So you need to be able to understand and evaluate how good your algorithm is doing, because otherwise you don't bring any benefit to your users at the end. So you have offline validations usually, measure under the curves, etc., on the limit test set. But the real testing is when you throw it to your user. And here, that's where things like A/B testing, tracking problems, be able to basically get the feedback from a user takes a very large importance. And it's actually, this cycle is exactly what happens when we want to bring this solution at scale. And each of every pieces of this are actually probably more important to solve than actually your algorithm itself. Here, Kens, I have led many different teams of data scientists in the past few years. And there's a generation coming up, which is a great generation, people that start to be trained with the algorithms, that understand how the algorithm work. And we have a wonderful tool called Kaggle, and that's basically a platform where you can have access to data sets, and you compete with the other data scientists to solve some problem, classification, regressions, typically, usually supervised machine learning. And this generation of people are very good with algorithms, very good with tricking, very good with overfitting sometimes. But what they're missing is that they haven't solved the problem I just mentioned. They are trained against very clean and labeled data set. And when I hire those people and put them in my team, they get super disappointed, because that's not the job that they will do as a data scientist. A data scientist, they're going to have to understand which data they need, how they can use it, how to clean it, how to prepare it, even before they can do a little bit of algorithm training. Data labeling is critical, and this is probably where the Chinese are a bit heads up on us, because first they are more, and secondly they are a bit more shameful about sharing everything, especially compared to Germany. But labeling your data is critical, because we're doing, again, supervised machine learning. So having access to ground truth or feedback from your users is actually essential. And if you don't get that, you just cannot do anything. You just don't have the data to be able to train your algorithms. So that's one of the first pain points that you will face as a data scientist in real life. The second part is that even for deep learning, you will have to be able to featureize, create features out of this data set that you have. Using it directly won't solve your problem, or it will be basically too raw. So you need to transform this data to create a feature, doing all this feature engineering to extract a higher level of abstraction of knowledge from the raw data to be able to apply it to your algorithms. And every data scientist will have to do that, and actually what will make a huge difference for all those Kaggle competitors is how good they will be in basically feature engineering. And this requires one thing that you don't get when you're out of the university as a computer scientist: domain knowledge. To do feature engineering, you need to understand which problem you want to solve. And that's tricky, and that comes with experience. Though deep learning has been a big buzz currently, and for good reasons. It's an extraordinary tool, but as mentioned before, it's a little bit of a black box, right? And to explain that to your CEO, when you explain to you that you have great performances, for him it's just like, oh, in the middle there's some magic happen. Please do some magic. I'm not Harry Potter, I'm not a wizard. I want to understand what's happening behind it. And that's the difficult part with deep learning. And sometimes it's very important for us to be able to explain to our peers. If you're a medical doctor and you're using deep learning to make some predictions, you want to explain to your patients why this decision has been taken. You're not going to proceed open heart surgery just by convincing your patient that, oh, yeah, but we have these fancy algorithms that decided that we need to do that. So somehow being able to predict why the decision has been taken is super important. We had a glimpse from Vladimir's presentation, how to make a decision. There's a lot of work going on currently in this concept and ideas. Try to understand how basically the neural networks are taking decisions. We heard the famous example of wolf versus huskies, where actually decision was taken because wolf has a background as snow. So there are now lots of work that's been done on explainable deep learning. This is one example. If you're interested, you can look at the article. It composes of two things. So you feed basically the algorithm with an image and one question, and what sport is this? And the algorithm is even able to basically tell you first why it took the decision, that it's baseball, here by highlighting the byte, but even able to generate text with an explanation to answer your question. So on the back is the PGX model, so it's pointing and justification model. It's based on different type of deep learning. So on the image part, it's a convolutional neural network, and then on the word part is the LSTM, so two different types of neural nets. And the idea here is that they have basically a first layer that helps them on answering the attention. So what is the part of the image that is dragging the attention of the neural net, and then convert that into a text, so explaining the attention. I could give a 1 hour long seminar on this, but if you're interested, just go on the link or discuss with me later. Another problem that we have is when you look at data, you not always have the right explanation, because correlation and causality is different things. And I have an example. My favorite example is not this one. My favorite example is that there is a very high probability that if you go to bed with your shoes on, the morning after you have a headache. You know why? What's vodka? All right? So there's no direct causality between the shoes and the headache. It's just because if you fall asleep drunk, you're most likely to fall asleep with your shoes on, and then you have a headache the day after. So there's a nice website, the Tiller Vegan, where it's basically collecting data from all around the place and process and look for weird correlation. So this one is a typical example. There's a strong correlations between the age of Miss America and the number of murders by steam, hot vapor, and hot objects, for instance. Obviously, there's no causality here. And there's a mathematical, actually, a theory that explains that. Like if you have enough data, you will be able to find correlation from anything with everything. Biases is the other big problem that we have. It's a plague, actually, for what we're doing, especially when you want to develop products. And there are very, very good examples of products that do not work because, again, supervised machine learning. So the training set has been biased. This one, it was a few years back. I think it's Snapchat that has those fancy masks that you could apply on your face that was not working on people with dark complexions. Why? Because all the training sample has been made by white, male, middle-aged engineers from Snapchat. One thing that will be great and will be very nice with deep learning is that if it could learn from the context itself. So this is Dory from Finding Nemo, and you remember Dory, the typical fish, has 2 seconds of lifetime, so she keeps forgetting about what she just did. Well, a lot of our neural nets are actually a bit like that. So some of them are trained at LSTM to learn a little bit from the context, but they're not very good at it, to remember, to learn from experience. And one thing that is very useful, and I use that a lot when I was in academia physicist, is that we have an intrinsic understanding of what's happening there. I mean, I've been studying galaxies all my life, and I have a good understanding of how it works. This intuition that I have, it will be great if we can implement it in there. And we have, mathematically speaking, something that is wonderful is Bayesian, because with Bayesian, you can basically twist the probability according to the knowledge that you have a priori. And there are lots of clever people now that are basically trying to mix Bayesian statistics with deep learning. I refer to this GitHub from Eric because I think it's a very, very simple and very nicely explained way of combining both. But on the top that we have is typically a neural network. So you have your vector input, and then you're trying to predict an output, all right, an outcome. And at the end, we can just see it as linear combinations of different weights and different biases with different functions. The mathematics behind neural nets, again, is not super complex. And here, the idea is that for your neural network, you have vectors that just with numbers, so the different weights, and we can transform that into basically probability distribution. So for each part of your link in your neural network, instead of having just one weight, you could have a probability distribution of weights. And this is a very, very good move forward, because then we can basically train our deep learning networks from experience. They can learn from previous experience. So we could basically transfer experience from one network to another. That's today it's not possible. The caveat of that is that it's extremely slow and very, very computing intensive. So I talked about deep learning quite a lot, neural net, but it's actually just one of the many tools that you can have if you want to try to use data to derive insights or to create products that will be of use for you, for your users at the end. And people tend nowadays to forget about those, but they are very, very, very useful. So the SVMs or clustering of all the classifiers that are out there, there's a full toolbox out there, and you shouldn't be ashamed to use it. Gradient boosting, decision trees. And as a matter of fact, in industry, there's a law, is that the more simple your algorithm is, the better it works at the end. Why? Because you have less engineering problems, it's easier, it scales better, it's better to maintain. So I'd rather have a logistic regression instead of a neural net in my classifiers for my 10 million users, right? Scikit-learn is basically one of the most complete library for machine learning in Python, and if you don't use it, you should. But at the end, you can also mix and match, be innovative. You can use some hybrid and use a little bit of this and a little bit of that and combine them together. You don't have to be dogmatic and just, no, I'm just going to deep learning, which is something that I find very often from freshers as well. You don't know, I just want to use neural net. I don't want to use anything else. But actually, at the end, you mix and match according to what is there, being pragmatic in implementation of your code in production. So when Christophe was doing his presentation at the end, he came up across to the most common problem that you will have when you use this type of algorithms. An engineering problem. In your case, that was easy. You solved it in a few minutes. But usually what will be hurtful when you want to use machine learning is the engineering context. And data science, machine learning, is before anything else, at least if you want to bring it in production at scale in companies, an engineering problem. So this is some sort of map. So I use that map very often to explain to my bosses the complexity of what we try to achieve. So in the middle in magenta, you have what we talked about today. So the core of things that you do with machine learning, those algorithms that you can train, optimize, etc. But this is part of a larger ecosystem. And this is what is data science in a company. My team is composed of 1/3 of data scientists and 2/3 of data engineers. All right? So the engineering part in data science is very, very important. And here you have basically collections of things I've already mentioned. So you will need to have an infrastructure. You need to run your code. That could be in the cloud. AWS of Google, but when you want to bring it at scale for several millions of users, that's a bit more complex than just running your notebook for yourself. So that needs to scale and work in all cases. You need to collect your data and manage it properly. You need to label it. You need to understand where it's coming from. You need to make sure that your tracking system is working properly, that you can get your feedback from your users. You need to develop internal tooling for people to use all those different bits and pieces. You need to verify and check the quality of your data. You want to automate as much as possible the process. And you have hyperparameterization problem. You have so many bits and pieces at the end in your different codes put together, especially when you start playing with ensembles of models, that you need to be able to configure all those magic numbers that Vladimir mentioned. And those magic numbers, they are coming out of practice. They're not in the textbook. You need to figure out what is the best number to use to choose the number of neurons that you will have in your neural net. Number of layers. Feature extraction I mentioned, analysis. Before any work in machine learning, the first thing you need to do is look at the data. Do I have the data? Can I answer the question I try to answer? A simple classifier, logistic regression at the start to be able to understand if you can solve the problem with the data you have. Because in 85% of the cases, it's no, you can't. You don't have the right data. Feature extraction I mentioned, and all the validation set, right? A/B testing is a major important tool, especially if you work in the internet industry. So, what we're trying to do at XING, and we're not the only one, is trying to make ourselves redundant. Humans are prone to make mistakes. The advantage of automation is that the mistake is always the same, so you can solve it. When it's done by human manually, the mistakes will change constantly. So we are building up our systems that are more and more and more automated, and that goes again even with the part of training the models. You can basically, if you look for this parameter, this 0.6 that you mentioned, Vladimir, in your presentation, well, you can basically do it pragmatically. It's just I will use my users to tell me what is basically the best number. How? I will just explore the entire parameter space automatically, generate many different models, and start testing it against my users and see which one works the best. Then I got the answer. And all that needs to be generated automatically. So the automation part is important, and it's actually probably currently 30–40% of what we're doing in my team as dedicated work. I mentioned that already, but begin one step further, incorporating something that I want to move to is the business part. As if I'm a VP of a company that generates several hundreds of millions of revenue every year, right? And I need to justify what every single step my team is doing. So we don't always justify in revenue, but we want to increase the traffic on the platform, for instance. So what we need to do when we think about developing new features, new algorithms, new functions on the platform is not to think, well, that would be cool to use your net, you know. That won't convince me. What do you want to do with it? What will be the impact for your user at the end? What will be the impact for the company? So we need to come up with some views and ways of constantly checking what is the impact of what we're doing. And come up with continuous delivery. So this is a lean way of working, that you develop very small feature and constantly test it and make some bet on what will be at the end the impact on the end users, right? On the company KPIs. So initially you will have an ideation phase. So, okay, this is a primary user have, how we're going to solve it, coming up with a small prototype, looking if your data is there, then create a minimal viable product. That basically takes a team 3 weeks to develop. Then put it into your system, throw it to your user, get an A/B test, and verify if basically the bet that you met. So I would say this particular feature will increase the number of active weekly users on my platform by 0.1%. And then I just throw it into an A/B test, and I looked if it happened or not. If it didn't happen, it's not a good feature, forget about it. If it happened, how I can make it even better. That's how you start developing cycles of production of machine learning at scale. I don't know how much time I have left, but evaluation, there are two types of ways of checking your the validity of your models. The first one is offline, and it's important to do both. So before deployment, you don't want to throw it to your user if you can know already by some tests internally that it's not going to work. So you have a leave and out evaluation. You can do manual examples, so picking up some of users and see if it works historically. You can do a more quantitative checks. You can do simulations, Monte Carlos, etc. But then the most important test is always online. Throw it to your user, A/B test. And you have many different technology that can be used for A/B testing. And A/B testing is hard. It's very, very hard. So you can do the classical A versus B, so it's basically the control sample and a variation sample, and just test against and see what happens. Or you can come up with a bit more fancy ways of doing things, like interleaving A/B testing, which will be, for instance, when you want to rank. So you want a search result, you're using a machine learning-based ranking algorithms based on the behavior, and then you want to know how good it is. So instead of separating by users, what you will do is that you will interleave results from your different machine learning algorithms in the same list and see statistically which one works the best, for instance. Why you want to do that? Because usually it's a better user experience. Because if you happen to come up with a model that doesn't work, then you will have 10% of your user that will have a very crap list of results, and that you don't want to do. So back to the automation. So we have at XING one of the most complex recommender I've seen on the market so far. I mean, I have the team, the core team, the 6-7 first people in my team are working on that for the past 8 years on Rexis. So we have a very, very complex ecosystem for a recommender. It's composed of many different small pieces, many different algorithms that we ensemble together. And then they generate a huge amount of different parameters that we need to check. So currently what we're working on is how we can go one step further, and instead of choosing manually those different parameters, is how we can basically have it thrown into our A/B test framework and have our user telling us which one of the parameters is the best. And just to give you an example for the job recommender, we have 800,000 job ads on average on the platform. We have around 500,000 weekly active users for jobs. And we have a hyperparameter space of around 200,000 parameters. So basically, it will take us forever to test all these parameters with our user base. So that's tricky. That's really difficult. One of the problems that emerged recently with machine learning is it's the replicability or reproducibility issue. It means that you will have 2 persons using the same data set with the same algorithm, and we'll have different results. And it comes to an extreme that we realize that it's really a problem. Be able to reproduce the same results using the same algorithm start to be a problem. And the reason is simple. It comes back to what I was saying before, is that your machine learning algorithm is just part of a big ecosystem. So you need to be able to track everything. What is the version of the library of scikit-learn you're using? Because that may create a difference. So the all metadata around basically your code is very, very important. So the code you're using is not the critical part. It's everything around. What is the data set? What is the test set that you're using? What is the training set you're using? All this will have an impact on your result. And worrying enough, and this is a graph coming from a recent report from last year, looking at AI papers, we realized that there's very little actual code that is published by the researchers. The main part of the code that is produced is pseudocode, or very little test data that are available. So if you have the hundreds of thousands of papers that have been published for the past 5-6 years in the field, very, very little, very, very often you won't be able to reproduce the result that they did. I'm a scientist, I'm a physicist by training. This is a big worry for me. It means that basically you have people doing research, they give you the result, and no one can reproduce what they did. And everyone is fine with it. That starts to be a concern, and that comes now to be able to control not only the code, So version controlling of your code, which is normal practice for software engineers, but go a bit one step further. Version controlling your data set, your training set, your test set, keep all the information. And that's again, something that it takes a lot of time and lots of efforts. So there are some companies, that's friends of mine from, so a bit of publicity for them. It's a bunch of Vikings from Finland, and they have this wonderful platform called Valohai, that means shark in Finnish. And it's basically doing that. So they try to bring one step further in the development. It's like the GitHub for machine learning development, where we can keep track of everything, including which data set you used. So when people ask me who wants to be data scientist, and they tell me, what is the future of our job? And it's like data engineers. Because we need, in general, far more data engineers than data scientists. And me, as a hiring manager, currently, that's my pain point. I mean, I have 6 PhDs in machine learning in my team, right? And the problem that I have is to find good data engineers. So if some of you here are interested in embracing a path in AI or whatever, choose the engineering option, you will land a better job. But don't only rely on your engineers. You go back to ecosystem, I've really focused on the engineering part, but actually when you want to bring a product that has an impact for your company and for your user, it goes far beyond just the technology solution. You need to understand the problem. You need to have your partners, different stakeholders in the company that can help you driving the right product. So there is a large ecosystem of different talents in the company surrounding data. Let's start with the data scientist, machine learning scientist, data engineer, but that goes down to your back-end engineer, software engineers, front-end engineers, product owners, business analysts, sales, all those people, marketers, they will have a role to play to be able to build a product that makes importance. And I used to be a rugby player. I just kept this from my times in rugby. I lost all the rest. But the Scrum looks like a pile of people. But in general, each person in the Scrum has actually a very particular function for it to work. And that's the way I see it, is that if you want to bring a product at scale in a company, you not only have to see the technology side of it, but you need also to see the business and the product. And you need to partner and create cross-functional teams across these different departments to bring a solution that works at scale. All right, so this is my summary slide. So, productivizing machine learning. Well, first of all, exploit all the tools. You don't have to use deep learning every single time. There are lots of other tools that can be used for machine learning, and you should basically consider them all. And honestly, simple is best. That's what scales better, that's what works engineering-wise better. So if it works, why do you want to make it more complicated? If it ain't broken, why do you want to fix it? Domain knowledge is critical, so there's a large fraction of the work that we do as data scientists, which is about basic understanding why we try to solve the problem, feature engineering. So you need to understand basically a good understanding of your domain. That's why we come to a more highly specializations of data scientists. Version control is not just for code. You need to be able to control the version of your training set, the libraries you're using, because otherwise you won't be able to reproduce the result that you see. Data science is an engineering problem, okay? It's not an algorithmic problem. It's really an engineering problem. You have to consider the entire ecosystem. Try to work with a continuous delivery. Small bits at a time. Ask your user, ask your user, ask your user. Don't wait for months to release a feature. Just do it every day. And finally, don't forget all the other stakeholders that you have in a company, because it's a cross-functional work. And if you don't understand the problem, if you don't understand the problem that needs to be solved, then you won't come with a solution that solves it, right? So you need to partner with the product owners and your business stakeholders to be able to do that. All right. So I'm Sébastien Foucaud. I'm the VP Data Science at XING. We are hiring. That's one of the main reasons why I came here today, just to advertise a little bit for us. We have many positions in technology and 35 minutes I did. Sorry. In technology, but also in machine learning, I'm hiring in my team for machine learning engineers, data engineers, and data engineers mostly. You can find me on XING, and if you dig a little bit, you can find me on LinkedIn as well. Thank you very much. I'm taking questions now.